explain question number 6. Yeah. This is about linear search. We have the number of elements 150, and we also have that probability number 0.8. The key that appears in the array, that probability. All right, yeah. And in our notes, we have the formula, right? You can find the formula in our notes. Yeah. Here, what I need, you apply that formula, you plug in the numbers. I like to have an exact number, okay? Do not give me approximate number, exact number, all right? That's the first thing. So you do not drop any term, okay? Keep all the terms, okay? Yeah, that's one thing. The second thing, yeah, one situation I had before, some students, after they plug in the numbers into that formula, they get an answer. But when they type the final answer in that small blank area, they drop the fraction because they feel the number of comparisons should be an integer. Here, let me tell you, do not drop the fraction. Do not drop the fraction. Why? Although the number of comparisons should be an integer, but here I'm asking you average number of comparison. Average. When you take average, usually you do not get an integer number. The average, you need to, do some division thing. So the final result, whatever it is, that's your final result. And we do not expect to get integer for average. For best case, worst case, then you are expected to give integer answer, right? Best case, worst case, just one case, right? Yeah. But for average case, you consider all possible cases. Then you take average. So you should not expect to get an integer answer, okay? Don't drop the fraction, the fractional part, okay? Yeah, so that's question number 6. Yeah. Question number 7, yeah. The polynomial, I give you the polynomial here. It is a 6-degree polynomial. Okay, yeah. So when you see this polynomial, I hope you can connect it to a special discussion we did in class, Pascal's triangle, all right? Pascal's triangle. Yeah. Because most of you may not be aware this question is related to Pascal's triangle. All right, yeah, because this polynomial is very special. The structure is very special. Yeah. If you cannot recognize the structure follows the Pascal's triangle structure, then you may not get correct answer. All right, yeah. So the first thing, you need to recognize the Pascal triangle structure. Second, after you get that step, so your expression should be quite different. Yeah. After that, then you need to use the repeated squaring technique. Okay, repeated squaring technique.
Observo.
Yeah. Okay. Yeah. So I hope you get it. So this is the hint I give you. Okay, yeah. Someone, yeah. Turning off the microphone. Yeah. One student, yeah. Susmitha, microphone. Yeah, all right, okay, yeah. I hope, yeah. So if you follow our lecture notes closely, yeah, it's not hard, all right, yeah. Okay, so that's the hints. Any question? Yeah, that's the two questions I feel you may need some explanation. What does belong to mean when refers to me? Oh, yeah, Cody, belongs to mean, all right, three categories, right? Yeah, here, I think you're talking about question number 5. 3 categories. In the class, in the notes, we mentioned that 3 categories: search problems, solve problems, selection problems, and the minimum, finding the minimum, that this one, it belongs to one of the 3 categories, right? Yeah, I just ask you which category does it belong to. Okay, yeah. So you look at our notes. Yeah, one of the 3 categories. Yeah, is it a search problem? Is it a sort problem? Is it a selection problem? Yeah. So if you have that answers for those 3 questions, yeah. So you can get this one. Yeah. One of the 3 types. Yeah. All right. Any other questions? So you can ask from in this chance. So you can ask. All right. Yeah. For question 1, yeah. The question 1, to evaluate polynomial, the higher the degree it has, the more multiplications we need. Here, I like you to tell me if the statement is always true, all right? If it is always true, yeah. The reason is this, because some students may feel sometimes it is true, then they feel, or most of the time it is true, then they choose true. Yeah. Here, what I need, if one statement is true, it must be 100% true. No exception, always true. Then we can treat it as correct, okay? If there is one exception, if you can find one single counterexample, then it is false. Then it is false, all right? If there is one counterexample, it is false, all right? Yeah. Okay, yeah. Any other questions? Yeah, I explained 4 questions. Yeah. If no other questions, yeah, so you just keep working. If you have questions later, Thursday, we have another chance. Before the deadline, Thursday, before the class, we have another chance. So I can answer your questions, all right, before the class. Yeah. All right, so let me switch to our new topic today, part B of module 2. All right. So let me start. New lecture. All right. Preparation a little bit. All right. Okay. Yeah. Part B. The topic is growth functions. The goal of this module, asymptotic notations. Yeah. But before I talk about that abstract concept, asymptotic notations, very abstract. So I need to do a lot of preparation. Yeah. And this concept, growth functions, another important concept before we can discuss asymptotic notations. Yeah. B.1, introduce growth functions. All right. First, let's look at this relationship. Look at the formula between running time and a number of basic operations. Why we need to look at this topic? Yeah. So the reason we like to consider the measure of efficiency of algorithms. Measure. Yeah. We talk about that measure at the beginning of module 1. We talk about that. Yeah. So we have some background about the measure. Yeah. Stable measure, right? Subjective, objective, right? We talked about that before. Yeah. All right. First, let's look at the notations. Yeah. For the running time function, we use T of n to represent it. Yeah. That n variable, integer variable, we know it represents the data size. Data size. Okay. The number of elements in the array, all right, so the number of data items. All right, yeah, data size. Function of the number of basic operations used, another function, C function, C of n, capital C. Yeah. But here you see this new concept called basic operations. So what is the basic operation? Yeah. The meaning, oh, sorry. Yeah. All right. The operation contributing the most to the total running time. For example, so if we use our first computing problem, evaluate the polynomials, if you look at that problem, we have two operations, additions and multiplications. But you can see multiplications contribute the most to the total running time, right? So then we treat multiplications as our basic operations. Yeah. So that's the meaning of this basic operations. Then I use another notation, execution time of basic operation, little c sub op. Okay, yeah, so this notation. With these three notations, then we can write a formula. But this formula is an approximation formula, not exact. Yeah. Because it's very hard to write exact expression sometimes. Yeah. So many times we have to take approximate expressions. Yeah. Here is the one. T of n approximately equals C op times capital C of n. Yeah. All right. Okay. Now, with this simple formula, next, let us study this formula. You can see, because this little C op, this is a constant. Okay? Yeah. It's a constant. It does not change. When the input variable n changes, C op does not change. So it's a constant. Yeah. then we can see T function and the C function, they are proportional. Their values are proportional. Okay, yeah. So that's the simple property we can observe. Yeah. All right, so then this kind of relationship give us a chance to use C function to measure running time function T of n. Yeah, we know running time T of n, that function is a kind of measure, right? Yeah, it is a measure. Yeah, good or not, but it is a measure, right? Yeah. Then with this approximation formula, we can use C of n to do the measure, because these two functions, they have the proportional relationship. Okay, so at least C of n is closely related to T of n with proportional relationship. Yeah. So, all right, so that's the first conclusion we get by observing this approximation formula. Yeah. All right. Yeah. Here, next, we want to continue our analysis approach. All right. Because in order to get a good measure, stable, objective, yeah, that kind of good measure, yeah, we like to try to find something that can give us that property. Yeah. All right, so the approach, ignore unnecessary details. Yeah. We try to ignore unnecessary details to simplify our expression. Simplify, yeah. The expression. Yeah, because after you ignore unnecessary details, your expression becomes simpler, much simpler. Yeah. All right. Yeah. So let's look at the questions. What information we can ignore? What information we treat as unnecessary details? First, can we ignore some constant? No. Constant. We may have some constant. Can we ignore some constant? Here, we are talking about C op, little C op constant. Yeah. By our intuition, we feel we cannot ignore, right? Because if you ignore it, the change is too big, right? The change is too big. That's our intuition. Think about if C op change from 2 to 1. Look at this change from 2 to 1. Do you think it's a big change? By your intuition, it's a big change, right? By your intuition, it's a big change. All right, yeah. But here in our algorithms discussion, we try to look at this question in a special view. We can change our views, right? We can look at the same thing in different views. Yeah. Sometimes when we look at the same object in one view, we get one conclusion. But if we look at from a different view, our conclusion could be different. Here, this is the situation. If we change our view, the conclusion could be quite different. All right. Yeah. So that's the hard part of this module. So a lot of things very abstract. Yeah. This is the hard part. Yeah. All right. Can we ignore some minor terms? That's another place we may consider if we can ignore something or not. Yeah. Last time, at the end of the lecture last time, I talked about that, 0.1% thing, right? The minor term accounts for about 0.1% of the whole running time. Yeah. So here we get to that question again. Yeah. All right. All right. But here, the first thing, two things we need to consider: ignoring constant, ignoring minor terms. So let's look at one by one. Yeah. All right. First, for the constant. Yeah. Here, C-op. Yeah. Let's just, put our attention at the C-op constant. If we can ignore C-op or not. All right. Look at this ratio. Look at this ratio. T of 2n over T of n. That means when you double the input size, 2n, double the input size, you get another running time function expression. Then you take the ratio. So this ratio tells us the increasing rate, how fast. Every time when we double the input size, the increasing rate can be described by this ratio, right? Yes, yeah, all right. The good thing is if we apply our approximation formula here, you can see that little C-op is canceled out. Little C-op, no matter it is 2 here or 1 or 3 or 10, the numerator and the denominator, they both have the same C-op, right? And this C-op is canceled out. That means that little C-op constant does not change the increasing rate. Increasing rate, no change. Yeah. Look at that observation. If there is no change, and if our main concern is increasing rate, then we can ignore that little C-op constant, right? Think about that. So you can see here, I changed the view. I changed the view from original absolute value, right? Yeah. If we look, here, let's look at the thing from two views. View one from absolute values. All right, yeah. T value, C value, absolute values. All right. View two, we change the value. All right. Not absolute values from ratio. Of, yeah, or, yeah, although it's a ratio form, yeah, although it's a ratio, yeah, sorry, absolute, all right, but actually it's from increasing rate, all right, yeah, as a ratio, yeah. So when we change to a different view, then our answer will be different. Yeah. From view two, then we can ignore C-op. Okay. Yeah. But that increasing rate is important, right? Yeah. So every time when you double the input size, how fast that function increases. That is very important. When we start, the function value is relatively small. Then the higher the increasing rate, that function usually increases faster, right? Yeah. So this view, this angle is reasonable, right? Yeah, in our description of the running time function. Okay, yeah, all right. Then, yeah, so in this special view, we can say that particular CR as the constant, all right, as the coefficient of that function, C function. Coefficient in front of that C of n function, that one could be ignored in a special view. How about that? This is our conclusion. Okay. All right. Now, after this discussion, so let's continue to the next step. Now we are ready to look at the growth function concept. Yeah. Because in this concept, we need to ignore that constant coefficient. We need to ignore it. All right. Yeah. Okay. So let's do it. Yeah. What is the major term in an efficiency function? Yeah. Efficiency function. Yeah. Major term, minor terms, major terms. Yeah. For the major term, we learned a similar term before. That's called a dominant term. All right, dominant term. The term dominates the function value, all right, in some way. Yeah. Which way? Yeah, we will see it. In which way it dominates. Yeah. All right. So let's recall the selection sort we did last time. Selection sort. Yeah. An array, and we use the minimum, finding the minimum of an array. That result, we solve it in this way. Okay. And we also know the total number of comparisons we need is this expression. Yeah. If we multiply out, we expand this polynomial. Yeah. This is a polynomial. Okay. We expand it. So we have two terms. The first term, 1/2 times n squared. And the second term, 1/2 times n. Yeah. Minus the difference of these two terms. And based on the definition of the dominant term, for a polynomial, it's very easy to find a dominant term. The term with the highest degree. Here, the square term, that's the dominant. So 1/2 times n squared, that is the dominant term. All right, yeah. And it includes that 1/2 coefficient. Includes that 1/2 coefficient. All right, yeah. Then from the dominant term, one step forward, we move to growth function concept. Yeah. Because when we define a growth function, we want it as simple as possible. We want to simplify it, make our expression as simple as possible. Yeah. All right. Yeah. Before we go to that, just one step, I like to explain how do we view the dominant term. Why you say it's dominant, right? Yeah. You may have this question. Why we say the first term dominates the whole expression. All right, yeah. So let us use some simple calculation in our calculus. Let's take the ratio, the first term over the second term, and we take the limit when n approaches infinity. This is a simple calculus question, right? Yeah. After we do simplification, 1/2 cancel out, and another n can be canceled out. So then we just get a simple n here. And when n goes to infinity, our answer is infinity, right? Yeah. So you can see the ratio is infinity where n approaches infinity. All right. Now think about it. Let us go back to our last lecture. At the end of the last lecture, I used that, concrete number 0.1% to explain dominance concept. Yeah. I said if the minor term only accounts for about 0.1%, do you feel comfortable to ignore that minor term based on our everyday life experience? Okay. Most of the time we feel okay, right? Yeah. Because here we are not doing something that requires really high precision, right? Yeah, like launching rockets, okay? Launching some moon landing type rockets. That situation probably you cannot ignore. Even 0.001 difference you cannot ignore. All right. But for our ordinary everyday life experience, most of the time we can ignore this small difference. Yeah. But here, look at the infinity. How big is infinity? Infinity, is it bigger than 1,000? Right? It is much bigger than 1,000, right? Infinity. So if we use 1,000, the first term is 1,000 times of the second term. Can you ignore the second term? All right. Another level forward, infinity is greater than 1 million, right? Think about that. Infinity is greater than 1 million. If the first term is 1 million times of the second term, can you ignore the second term? Yes. Yes. No problem. Yeah. So that's the reason. Yeah. So this view, this computation result justifies that we can comfortably ignore the minor term. How about that? Okay. Yeah. Although if you look at it here, if you look at the absolute value, the second term could be big, right? 1/2 of n, because n can be 1 million and n can be 1 billion. So if you look at the absolute value, it is huge. All right. Yeah. But after you take the ratio, the first term really dominates the second term. Okay. Yeah. So you don't worry about, if we simplify the whole expression by ignoring the second term, if that step may cause some big problem, so you will feel comfortable, because we just ignore less than 1 millionth of the dominant term, right? Less than 1 millionth of the dominant term. How about that? Right? Yeah. All right. So I spent a lot of time here. Yeah. Yeah. My goal, my purpose here, I just want you to feel comfortable when you ignore the minor terms. Yeah. So that's my, objective. All right. Then move to the growth function. From dominant term to growth function, we ignore another piece of information. That is the constant coefficient. Here it is 1/2. We ignore that 1/2, then we move from the dominant term to the growth function. Yeah. So this n squared becomes our simplest expression. Yeah, n squared. That's the simplest expression we can have to describe the efficiency function for the selection sort. Just n squared. Look at that, n squared. All right. That's the growth function. Yeah. So with this much discussion, you can see we get the growth function. All right. Yeah. Later, when I ask you, when I talk about the growth function, this term, you, in your mind, so you connect. And the first, you connect to the dominant term first. Yeah. Just take the highest degree term, the term with the highest degree. Yeah. After that, then another step, dropping the constant coefficient, dropping the leading constant coefficient. Then you get that growth function. Yeah. Why this growth function is important? Later, when we do comparisons, later we need to compare the efficiency of two algorithms. How do we do the comparison? We compare their growth functions. Yeah, you will see we compare their growth functions. Yeah, so that's the reason it is important. All right, yeah. And when we move to our next topic, part C, so I will introduce asymptotic notations. When we use asymptotic notations, we will use growth functions to define asymptotic classes of functions. Yeah. All right. Yeah. That's this concept. Yeah. Next concept, next step, B.2, compare growth functions. Yeah. Before we move to part C, asymptotic notations, let me do comparisons between two growth functions. Yeah. Actually, this part is the continuation of our previous algorithm. Recall, we did a computing problem in the previous lecture. So what's that problem? Okay, yeah, so recall that problem. Yeah. It's called element uniqueness problem. Element uniqueness problem. Right? In that problem, we find two solutions, right? Method 1 and method 2. Yeah. And we find the efficiency functions of those two methods, but we didn't do comparison, right? Yeah, we didn't do comparison. So here, let us do comparison. Let us compare the two growth functions for that problem. Yeah. All right. Compare two growth functions. Right. Which method is better? Yes, because that comparison will tell us which one is better. Okay. Method 1 is better, method 2 is better. Method 1, we apply the brute force. Method 2, we organize the data by sorting the elements first. So remember? Yeah. All right. So let me just copy the result from method 1, the worst case function. Yeah. Not the best case, the worst case. We compare worst case functions for both methods. Yeah. The first expression, 1/2 times n minus 1. Second method, we have n log n, the major term, the dominant term, and the plus the minor term, n minus 1. Yeah. All right. Next, when we do comparison, we need to get their growth functions first, because the growth function is the simplest expression to describe the individual efficiency function. Yeah. So the first growth function, n squared. Yeah. The second growth function, n log n. All right. Let us do comparison between these two functions. Yeah. How to do the comparison? Use ratio. Yeah. Ratio. Yeah. Limit. Yeah. the same way we did in the previous slide, limit of two functions, and when n goes to infinity, we calculate the limit. So let us do the calculation here. Yeah. When n approaches infinity, n squared over n, what is the limit? Here we need to use our calculus. I hope you still remember the calculus part, how to find this limit. Yeah. Let us do simplification, cancel 1n, numerator, denominator. Yeah. So we get a simplest expression first. Next, how to find this limit? How to find this limit? Yeah. Here, I may like to use two methods to look at the answer. Yeah. All right. The first one, this log. What is the base of this log? Right? Yeah. I didn't put a base. Yeah. So here we can assume for any base a that is greater than 1, we can use it. A greater than 1, yeah, we can use, we should get the same answer. Okay, yeah. And the answer is infinity. N over log n is infinity. Yeah. Can you see this answer easily, in a comfortable way? Infinity. Yeah. How to see it? Yeah. So I like to use two different ways. Yeah. Yeah. I hope I do not spend too much time. Yeah. All right. So method one, we can do some variable substitution. Variable substitution. What kind of variable substitution? Yeah. Here the numerator, denominator is log n. It's a log. Yeah. Yeah. Because sometimes we feel it is not easy to deal with the log function. Yeah. So we want to do some substitution to avoid log function. Yeah. All right. So let us introduce a new variable called a u. U equals log base a of n. Yeah. So if we use this new variable, then we can represent n as a exponential function, base a exponential function, but a greater than 1, a to the uth power. Yeah. All right. Now our limit expression of the ratio becomes limit of a to the u over u when u goes to infinity. New expression. Yeah. Can we see the answer much better than before? Right? Here the denominator is just a linear function, u, linear function. And the numerator is an exponential function. Can we say the exponential function with base greater than 1, exponential function, its value dominates the denominator function. Denominator function is a polynomial. It's a simple polynomial. It's a linear function. Yeah. And its answer is infinity. Yeah. But we need to use this fact that people realize, yeah, in our everyday life, an exponential function dominates any polynomial. Exponential function. Yeah. All right. Yeah. Increases much faster than any polynomial. Yeah. All right. So that's one way to view the answer. Yeah. But there is another view. We need to do more computation. L'Hopital's rule. By L'Hopital's rule, we can find the answer, actually, we can do more computation on the previous limit. Previous limit, exponential function over a polynomial. Why you say it's infinity, right? Yeah. Because some people may still want to get a rigorous proof, not just by our everyday life experience. They really want rigorous proof. Now, that's from your calculus. So you can find from your calculus textbook that computation of that limit. Yeah. But here, I don't mind to do it another time, but this time I use the L'Hopital's rule to calculate the limits. I hope some of you still remember this L'Hopital's rule. Yeah. In your calculus 2, not calculus 1. Yeah. This is part of calculus 2. Yeah. All right. Limit of ratio of two functions. When we calculate limit of ratio of two functions, L'Hopital's rule tells us under some special conditions. Here I skip condition, but condition very important. Under some condition. Later I will talk about that condition. You need to check the condition first. Under some condition, then we can calculate a different thing. So that's the limit of ratio of two derivatives. Then we will find our answer relatively easier. Yeah. That's the L'Hopital's rule. All right. All right. Yeah. So that when we talk about the condition, that condition related to a concept called indeterminate form. The condition is related to indeterminate form. You need to check if the ratio is an indeterminate form. So what's the indeterminate form? One commonly used indeterminate form, infinity over infinity. Infinity means the numerator approaches infinity. Denominator also approaches to infinity. That's the first indeterminate form. The second, 0 over 0. Second indeterminate form. Okay? Here we're talking about form. Do not treat these two things as numbers. They are not numbers. They are forms, special forms. All right. Okay. Let us check our current form we are considering. A to the u over u, is it an indeterminate form? Yes. The numerator approaches infinity when u goes to infinity. Similarly, the denominator also approaches to 0. Yeah, approaches 0. All right. Yeah. So we have no problem to apply the L'Hopital's rule. Yeah, let us work on it. When we apply the L'Hopital's rule, we need to take derivatives. The derivative of the numerator, that's easy. It's 1 by the power rule. Power rule. Power rule, you apply derivative of the power function. Yeah, this is the power function. Yeah. The power rule tells us the derivatives of a power function equals this. Okay. Yeah. K times x to the k minus 1. Yeah. K is not necessarily an integer. Yeah. K, we only need, it's a real number. Okay. Real number, but not 0. Okay. If it's 0, you cannot apply power function. A not equal to 0. K could not be 0. K could be negative number. It's okay. Now, for the power rule, K is allowed to be a negative number, but cannot be 0. All right, yeah. Oh, just a minute. Yeah. All right. Yeah. All right. Yeah. Okay. Then, oh, the numerator. Derivative of numerator, you can find this formula. Yeah. Natural log of A times the original exponential function. Right? Then we apply L'Hopital's rule. We can see the numerator goes to infinity, denominator just 1. So our answer is infinity. Yeah. So that's the L'Hopital's rule. Yeah. Later, we will have many questions. We need to use L'Hopital's rule to find the answer. Yeah. I hope if some of you are not familiar with the L'Hopital's rule or pretty much forget that part, so you can do some study a little bit. Yeah. All right, so let's continue. Yeah. All right. Yeah. Yeah, here. Yeah. I like to point out a special case because here there is a step we need to take derivatives. Yeah. So this step we need to take derivatives. When you take derivatives, how can you take the derivative of a function? That function must use a continuous variable. If you use discrete variable, yeah. So what I mean, if you use discrete variable, yeah, for example, n squared, can you take a derivative on n squared? You cannot, no. Because that n is discrete variable. The value for the n, 1, 2, 3, that's discrete values. There is no definition for its derivative. Okay? Yeah. But when we look at x, then we can take it because x, it takes continuous value. All right? Yeah. Real numbers, continuous. Okay? Yeah. Not discrete. Yeah. So that's another important thing. If we need to do rigorous calculation, rigorous. Here, I emphasize, our computation should be very rigorous. All right, yeah. Here, let me give you an example because we may need to consider limit for this one. Yeah. This is the, when we compare two growth functions, we get this ratio of two growth functions in a direct way without using variable substitution. Yeah. So this one is the, original ratio. Okay. Yeah. This one, not original, right? After variable substitution. Yeah. But this is the original one. Yeah. Here, we may like to do the calculate this limit on the original form directly. How about that? As an exercise, let us apply the L'Hopital's rule another time on this limit, original one. Yeah. But this time you can see numerator function and denominator function log n, they both use discrete variables, right? Yes. Be careful for the discrete variables when you want to apply the derivatives, you may have some problem. Okay? Yeah. So how to solve that problem? Yeah. Derivatives for discrete functions do not exist. That problem. We want to avoid that problem. All right? Do not exist. Yeah. All right. So here, yeah, the discrete variable. Yeah. So our method is, yeah, all right, I have to erase. All right. So our method is we consider a different limit, but we change from discrete variable to continuous variable. How about that? Numerator function, we change from n to x, but our x becomes continuous variable. Similarly, the denominator function, we change it from log of n to log of x, and with continuous variable. After this change, then we have no problem taking derivatives. Yeah, so let us take derivative. Derivative of x, that is 1 by the power rule, okay? By that power rule. Derivative of the log function, 1 over natural log of a times x, okay, as the denominator, reciprocal, okay, a reciprocal function. Yeah, after simplification, we have this expression, and then when x goes to infinity, yeah, remember a is greater than than 1. If a is greater than 1, natural log of a, here I talk about a greater than 1. The natural log of it greater than 0. So it's a positive number. Positive number times x. X goes to infinity. So the answer is infinity. All right. So you can see after we change from a discrete variable to a continuous variable, we get around that limit problem, limit existence problem. We get around it. So finally, we find it. So this limit equals infinity. After that, then we go back to our original limit. Can we go back from x expression back to n expression? Yeah. Because expression, that is different from our original expression. So we need to go back. Yeah. But when we go back, we can get a conclusion, our original limit also infinity. Can you see the bridge, the difference? Yeah. Y from x form limit to back to n form limit, because if this is true, when x approaches infinity, that ratio of two functions is infinity. Do you know how do we approach infinity? When x goes to infinity, how to make x go to infinity? Can you see that? How do you make x go to infinity, right? Yeah. By the limit definition, any way go to infinity is okay. Any way goes to infinity is fine. All right. So anyway is fine. All right. So here, let me write. Okay. Anyway to infinity is fine. All right. Can we take a special way, the discrete value way, 1, 2, 3 way for to infinity? The discrete way also fine, right? Yeah. So because anyway is fine, then this consecutive integer way is also fine, right? We take consecutive integer way to approach to 0, to approach to infinity. It's also fine. It's just a special way, okay? Consecutive integer way. Yeah. Then, so this direction deduction is also correct. All right. So here you can see, in order to do rigorous math here, so then I go to the continuous variable, then come back to our discrete variable as the conclusion. All right. So the conclusion here, yeah, the algorithm with growth function n log n is faster than the one with growth function n squared. That means method 2 is better. Yeah, so n log n, that's the method 2 is better than method 1. Okay, yeah. Yeah, better. All right, yeah. Okay. Yeah. So we solve that element uniqueness problem completely. Element uniqueness problem completely. All right. Yeah. How about that? All right. Think about, is it too much work? I spend a lot of time because there are many concepts I need to explain. Many little things we need to pay attention. Discrete variable, continuous variable, L'Hopital's rule, derivatives. You can see so many concepts we need to worry about. Indeterminate form, right? Yeah. Infinity, right? Yeah, all those things. Yeah. All right. So we complete this topic. Yeah. All right. Then we only have a few minutes left, not too long. Yeah. Yeah, but I have another topic I want to talk about before, and I couldn't finish. So I like to use this chance to complete that topic. That is the repeated cubing technique. Yeah. I give you repeated squaring, but there is a similar technique, repeated cubing technique. So you can see we can apply the similar idea. Yeah. But the result is quite different. Yeah. So first, the problem we want to work is calculate the monomial x to the nth power. Okay, x to the nth. Yeah. X to the nth, yeah, by the repeated squaring. Yeah. So let's start from the repeated squaring. Yeah, sorry. Yeah, repeated squaring. This technique, we know when n equals power of 2, it is very fast. Right? So that's the conclusion we got before. All right. So then what the conclusion we have here? Okay? What is the conclusion we have here? The conclusion is, yeah, repeated squaring technique favors the structure of power of 2. N equals power of 2. This structure. All right. Yeah. That's natural. Yeah. Power of 2 squaring. Yeah. So now the question. Now the new question. How about power of 3 structure? Right? When we change the structure is different. 3 to the kth. Structure is different. Then repeated squaring may not be good. Think about that question, right? Yeah. The technique and the structure do not match. The repeated squaring, that technique does not match the structure n equals power of 3. Is that possible? Yeah. We like to do experiments. Okay. All right. Yeah. So let me just try one example, yeah, because we do not have much time. So I just try one example quickly. All right. So n equals 3 cubed. That is 27. How about that? So now let us calculate x to the 27th. How many multiplications do we need when we calculate x to the 27th? Yeah. First, repeated squaring. Okay? Yeah. Squaring way. All right. Okay. Yeah. All right. X squared, the first multiplication, x to the 4th. Second, I just put a 1. Accumulative way, x to the 8th, another 1. X to the 16, sorry, x to the 16, another 1. All right. Then, how to get 27? 16 plus what number, 27? 16 plus 11, right? Okay. 16 plus 11. 11 equals 8 plus 3, right? Yeah. 3 equals 2 plus 1. How about that? All right. Yeah. So then, to get this one, we need to use x times x squared times x to the 8th times x to the 16th. All right. Yeah. 1, 2, 3. So here 3, but we need a 4 here. All right. Yeah. So the total, yeah, equals 4 plus 3 equals 7. 7 multiplications. So based on the repeated squaring technique, we need 7 multiplications. Second, cubing this time. Because we know cubing matches the power of 3 structure, right? Think about power of 3 structure. So we should do much faster. All right. X times x times x equals x cubed, right? 3. Here we need 2 multiplications. All right. Then x cubed times x cubed times x cubed equals x to the 9th, right? Another 2, okay? Yeah. The last step, x to the 9th times x to the 9th times x to the 9th equals x to the 27th. All right. Another 2, right? Look at that. 2 plus 2 plus 2. So the answer equals 6. How about that? Compare 6 and 7. 6 and 7. Look at that. Our first experiment, we need 7 multiplications. But our second method experiment, we need 6 multiplications. 1 fewer multiplication. You can see for the power of 3 structure, repeated cubing is better. Or we can say we have a similar conclusion, that is the repeated cubing technique favors the structure of power of 3 for n. Power of 3 structure for n. How about that? Okay. All right. So that's my, last topic, repeated cubing technique. All right. So I just finished our part B of module 2 today. Yeah. All right, so we complete our Zoom meeting today. Yeah. That's it.